Good morning and welcome to a marvelous Math Monday. And let's get started on some trigonometric functions, or periodic functions we'll start first. And so if we had a situation where we wanted to model data like this, where we have the scores on the SAT, the Standard Aptitude Test. This is data from the United States, of course, because you won't write the SAT unless you're planning on applying to American universities or American colleges. But here we have SAT scores, and they're divided into two categories, the verbal and the math. And we notice that the students that tend to score higher on the verbal scores also tend to score higher on the math scores. And the 10 people that score lower on one tend to score lower on the other. What kind of parent function would you use to create a curve of best fit here? Yeah, it's going to look like some kind of y equals x would be the parent function. And then the transform versions of this just look like y equals some slope times x plus b. And we can think about both of these as a transformation, right? If we had f of x equals x, and then we wanted to write this in transformation notation, we create a new function that's going to generally model what we're seeing here. We would probably have, would you agree that the y-intercept would be somewhere around 490? And that the slope there looks almost 1-to-1? Like as we go up here and we hit a math mark of 580, we're hitting a math mark there of about 590. So that's about 1-to-1 with the rise and the run. So our transformation, if it wasn't, we would have g of x being equal to some number a, which would be our m, multiplied by f of x, and then we would be adding some number c. It would be an a and a c transformation. Suppose this slope, if we increase by, let's say here, we'll go from 500. Oops. Let's take a look at our rise and our run, and we'll just design it so that we don't get a... So there I run 40, and how much do I rise? So that's a run of 40, and I would rise from about 510 to about 540. So that's a rise of 30. Morning, Mr. Rayner.
Good morning. How you doing?
So there, our rise over run is 3/4. And that would tell us that we need some transfer, and our b value here, b would be equal to 490. So we could create a g of x, some function that's a transformation of f of x, that would be multiply it by 3/4, multiply all our outputs of f of x, and then add 490 to them. Good morning, Action. So that would give us a proper y equals mx plus b that would model that behavior. Now, here is an example of data that follows another pattern. If we wanted to create a curve of best fit, here you have a measurement of temperature and then the amount of electricity used to maintain that temperature. This should make intuitive sense. If the temperature that we're trying to maintain inside is close to the ambient temperature outside, it will take less energy. If we're trying to cool things down or we're trying to heat things up, it's going to take progressively more energy on either side. So what shape do I have here? What parent function would I use?
Y is equals x squared.
Yeah, the quadratic parent function, so we would use a y equals x squared. So that's our f of x is equal to x squared. And if I wanted to transform this parent function to fit this data, well, I could do it in standard form, but I would probably be easier to think about this in terms of the vertex form of a quadratic. So let's find the vertex here and then think about our stretch factor. And we're going to just go approximate here. I'm not going to do the algebra for you because this isn't our main topic. But here, looks like our vertex in the x is about 16. And in the y, you could call that 11. So there would be the point 16, 11. And so I want some transformation that's going to move that over to the right and move the vertex up, because y equals x squared, that vertex would be here. Okay? But actually, let's draw our parent function in a different color here. So here's y equals x squared. Got to be something like this. It's going to be much steeper than that. Sorry. But let's put on our points here, 0, 0, and 1, 1. So we know that 0, 0, and 1, 1 are going to be on the parabola. There we go. And so now we can think about this as a series of transformations. First, we've got the C and the D. So let's put those on there. But we also want to think about our A transformation. So this point here, 0, 0, it wouldn't be affected by A or K. It moves over 16 and up 11. So I'm going to need some D and C transformations here to create G of x. So G of x would be a transformation of f of x. We're going to have some stretch factor over there. We're going to find that by playing with the point 1, 1 and transforming it to this point over here. But f of x is going to be, we're going to have to do something to the x value and add a C transformation. So we're going to have a D and a C. What C do I want if I want to move this vertex up to 11? So I'm going to be adding something to all the outputs of the function. What would I be adding to all of them if I want this vertex to go from 0 to 11? Yeah, I'm going to add 11 to all the functions, to all of the outputs. And then to the x values, I want them to be moved in the positive direction by 16. So what do I do to the x values here? Suraj? Here I have to subtract 16. Remember that my D transformations, when I'm subtracting from inputs, they are sign flippers. Okay? And then I need to stretch the function as well. If I know that 1, 1 is on the parent function, let's go over by value 1 from here and see how much did it increase. And probably if I go over by 1, I'm just over here. I'm just a little bit higher. Call it about a quarter. Call this the point 17. 11.25 on the new function. So instead of going up by 1, it went up by a quarter. So there, I can just stretch the whole function by a quarter here. Multiply all my outputs by a quarter, and that will create this new graph. And so what I would have is a function that would look like g of x is equal to 1/4 x minus 16 squared plus 11. And that's a parabola in vertex form that might model this data. And that's what we're doing with these functions, is we're often modeling data that we're going to find. We're going to create a curve of best fit. And later this week, I'll actually show you how to use Desmos to create very accurate curves of best fit given the table of values. But this would be eyeballing it, ballparking it, and getting a curve that goes through that data. Now, what if we had a situation like this one, where you have the amount of trout in a particular lake? It starts up here and it goes down. What's this an example of? What would our parent function look like? Would it be linear, quadratic, sinusoidal, absolute value, square root, exponential?
I forget what it's called.
Yeah.
Square root value.
The square root wouldn't fit it too badly, would it? It would look a lot like the slide over there. But then one thing that you can think about is the domain and range of a square root function. And with the square root function, so the square root function generally looks like this, right? Where it starts and it goes up and then it starts to grow slower. So Jonah is imagining, well, if I flip that, it would be down here. So I have a negative a as my first transformation. And then I'm going to lift all of the points up so that it follows along this way. Right? Something like that. So that's like negative a to transform it so that it comes down, and then translate the whole thing upwards. Cool. But is there any limit to the upper side of that function? No. So it, even though it grows slowly in the vertical dimension, its range still goes to infinity in that way. So can we have a concentration of trout that is negative? No. So we want some function that has an asymptote, something that will approach but not pass a certain line. Dave? Oh, okay. So absolute value would come down to 0 and then bounce up again. Right. Suraj?
Exponential.
Yeah, so this is going to be an example of exponential decay. Right? So we have an exponential decay here. So we're going to have some function as our parent function. F of x would be equal to, and we could use 1/2, sure, and we can make it fit 1/2 raised to the power x. After a certain amount of time, this will be half of how big it is. And then after a certain more time, it's half again smaller, and then a certain more time, half again smaller. And so our transform function would need, this would go through here at the point 1. So we're going to need to stretch it up by factor, say, 16. So that would be like 16 as an A transformation, a vertical stretch. And then we would also want to find the half-life, and we would put that in as a K transformation. So it would be x divided by the half-life here. So I go 16, and then I'm just going to find where does it look to be about 8. And it looks like if I clear these ones off where I was just thinking about square root functions, and I draw my curve of best fit here, so, and I look for, where is that about 8? And it looks to be about there. Okay, that looks to be about the point 5 years. So 1975, we started at 1970. 5 years and the point 8. So I can label that 8, 5. And this would be the point 16, 0.
I think it's the other way around. 5, 8.
Thank you. Yeah, I'm doing that X and Y inversion thing that I sometimes do. That's 0, 16. Thank you very much. So that's 0 years in the X and 16 parts per million trout, 16 trout per million. And then this is 5 years and 8. Okay. So in that case, I would be dividing by 5 here, and that would create this half-life situation where every 5 years I multiply 16 by another half. And this gets smaller by half. After another 5 years, goes down to 4. That looks about right. After in 1980, it's about 4. Here it's about 2. And there it's about 1. Cool. Okay, so that seems to model this behavior very well. Exponential function, we see this exponential decay. And the reason why I prefer exponential rather than square root is because if we look at the end behavior, if we were to go out in this dimension further, a square root's going to pass 0 and keep going into the negatives, and that just doesn't make sense with our data. So probably something that makes sense going into far into the future is going to be a better model for us. It's like, have you seen, oh no, that's too far of a tangent. I'll talk about that another time. So, another thing that we need to do. Who's wearing flannel today? I just looked down, saw myself, was like, you're dressed funny today. Oh yeah, who's wearing flannel? Riley is. Who else? 1, 2, Julie, very good. Myself 3, Liam 4. Peter, is that a hand up? You have something flannel on? No? Okay, so we have 4 people in compliance with the Spirit Week today. To let me review what the Spirit Week is at some point today. Remind me to show you, and because we'll get a prize on Friday. We've got a big class, so we can get a lot of people who are following along, and that way we could win ourselves a prize, something on Friday, something exciting. I don't know what it is. Well, because I don't know what it is, I'm even more excited than if I knew. But if we had things like these, do we have any parent functions right now that could model things like this? No. We have some data here. This could be this is time in days. This is something that rises and falls. We don't have any functions that will do this, that will go up and come back down again, and go up and come back down again. Suraj?
We have like sine, cosine.
We're going to be particularly using sine and cosine to model these types of behaviors. So this is the type of function that we're going to need this for. For these, here, this is perfectly following sine and cosine. Our curve of best fit goes through all the data points, reaches a maximum and comes back down, and so on. And that's taking it through here 2 periods, 2 cycles. There. This data here, it comes down slowly and then rises quickly, and then comes down slowly and rises quickly. So this could be something like the temperature, which might rise quickly in the morning and then fall slowly throughout the day, something like that. These can still be modeled with sine and cosine. That's just a topic for you to look at when you're in university to model those. We can even start playing with those ideas now. So today we're looking at periodic functions and their properties. So on the handout, which you will receive tomorrow, but you could take this down in your notebook now, you're going to want some definitions. So periodic functions are functions that have a pattern of y values, a pattern of outputs that repeat at regular intervals of x values. So we have some kind of repeating data. This is the most important part of what makes a periodic function. We're going to have some repeating data and some pattern that repeats in the data. So something like this is data that repeats. Something like this, oh, that's pure data that repeats. This is actually a sine wave in radians. So there is the value pi, and there's the value 2 pi there. So that's in radians. These two would be example of periodic functions. They repeat regularly across their domain. As we look at a wide variety of x values, we're going to see a repeating pattern. Periodic function, that's what that is. Now this here, this is not a periodic function. It does contain a periodic function, but it's not a periodic function. Can anyone tell me how I could get Desmos to produce something that looks like that? Anyone have any ideas how to do that? Shall we go take a look? It'll help us when we're doing our art if you know how to say, well, how would I get this? Like, it's the same. It looks as people can see that it looks the same as this one, right? But it's a different, something different going on. Like there's this here. Siraj, what would you do?
You have like the a subtracted by the x, so that as like the x is getting larger, then the a is also.
Oh, that's interesting. Yeah. If I had, but that's going to give it. It's going to go down as a line, and it's going to go to 0, and then it's going to flip. Okay. So, yeah. Do you see what you do need to do there yet? No? Okay, let's go take a look. So we're going to play with this one in Desmos and see if we can get that to happen. So here, first of all, it's periodic function day, so we do want to take a look at, what is f of x equals sine x look like? And this is going to be, we're going to spend a fair bit of time with this fellow here. Let's make it such that, yeah, you can see it pretty well there. There's a sine function. Now, if I apply some transformations to f of x, so I'm going to create a new function g of x, and I'm going to say that's equal to, well, Siraj said one of the first things you're going to want to do is multiply all of my outputs by something. So let's add a slider for a. So here's my a transformation. And as I transform that and make a bigger, this gets bigger. This is still a periodic function. It still regularly repeats. If I want to change it for something that doesn't quite regularly repeat, let's do this. Let's also multiply it by, so there I have it up to about 4. Okay. So if we were, this is the function that we're trying to recreate, something that has a very wide in the beginning and then gets very small. So let's multiply this also by an exponential function. So I'm going to have 1 over 2, and then I'm going to make sure that my bracket is in the right spot, and I'm going to raise that to the power x. And now that is happening too fast, so I am going to divide x by, let's say, 10. Now, when I look at this, I have a function that is shrinking as it grows throughout its domain. If I zoom out for you, you'll be able to see that this looks fairly similar to the function that we were just looking at, where I have this periodic behavior, but it's getting smaller because I'm multiplying it by exponential decay as it goes down. If I change that to 100 there, it's slower. Okay, so that's that type of function created there. I can look at this because I can see that the maximum values there are decaying exponentially. I just decide I'm going to multiply the whole thing by an exponential decay and get that to do that. This one here, this is periodic, but this has a periodic oscillation to it, but it doesn't have the same periodic pattern. How would you create this type of function? Looks like I'm putting two functions together. What could I do to create something that looks like that? Let's try it again in decimals. Here, if I take f of x is equal to sine x, and let's zoom back in so we can see that a little better. Hey, going the wrong way. Over here. So here is f of x is equal to sine x, but I want that to rise. So if I said f of x equals sine x plus x, there. It's a sine function plus a line. So that one's pretty easy to put together. I want it to oscillate, but I also want it to grow according to a line if I want it to recreate this here. So these can be assembled, they can be put together. Now, one of the things that we're going to be looking at is the cycle of a periodic function. This periodic function here, this could be the model of like a sawtooth blade or something, or this could be a sound as well. It would be a fairly boring sound to hear. It would be very unpleasant to the ear because it's so harsh and jagged. It's an example of like a sawtooth-like wave, but it could be a sound. And a cycle here is one complete pattern on a graph. So here, if we say this is the starting point there at 0, it doesn't have to be the starting point there. In fact, we could say this is the starting point as well. From here to here, this is one cycle. Going from there to there. One cycle from here to here. So a cycle is one full walkthrough of that pattern. One full example of the pattern that's repeating periodically is a cycle. And the period is the length, the amount of distance you have in the domain for one cycle. How many x values comprise one cycle? So in this case, if this is starting down here at looks like about minus 6 and a bit, and then goes up to 0, and then continues from here and goes up to 6 and a bit, you would say the period, the way you would calculate it is the x value at the end of the cycle minus the x value at the beginning of a cycle. So let's use some easy ones to keep it easy for ourselves. We'll call this the point 0, 0, and then this the point 6, 0. And this is the 0, 0. So if we want to know the period of this, we would say that that's 6 minus 0 equals the period. So it would just be 6. 6 is our period here. And that's one of the important things, to be able to look at these periodic functions and know how long does it take for it to repeat once. Another thing that we'll have here is that these functions have an axis, but unlike the axis of a parabola, which is vertical, these tend to be symmetrical or repeating around a horizontal axis. So we want to be able to look at these and say, well, what's the maximum value here and what's the minimum value? So the minimum value, and these are y values, this is the output here, 0, 0. So it's outputting 0 down there for x input of 0. And then up here at around 1, or in between 1 and 4 there, it looks like, it has a value of, we'll just say 2, 0 there. Sorry, 2, 3. It's 3 in the y. That's a 3. So the equation of the axis is going to be the maximum, the 3, plus the minimum divided by 2. It's just the average of the highest point and the lowest point. So that's going to be right in the middle. That's going to be at 1.5 there. So there, if I want to know the axis of this function, it's there at 1.5. That's y equals 1.5 is its axis. And the amplitude. This is the last thing that we need to know. Again, it's the maximum minus the minimum divided by 2. And it's always a positive value. It means what's the distance between here and here, but half of that distance. So again, this is going to look like the equation for the axis, but here we're measuring more the distance from the axis. Another way to think about amplitude is if I draw the axis there, the horizontal axis, that will by definition be the same distance to the bottom point as it is to the top point. What is that distance? Gives me the amplitude. So here again, if I take the maximum and subtract the minimum and divide by 2, that's going to give me, give me that value, 1.5. In this case, the amplitude happens to be the same thing as the axis, but that's not always the case. Let's go back now and take a look at our sine graph. And we're just going to take a look at, I'm going to remove that linear component. There we go. If I zoom in on this one, we'll see, and we're going to be spending a lot of time with this fellow. Notice right now that my graph is in radians, and our course, we work in degrees. So I'm going to change this to degrees, and wow, did that ever flatten out, eh? So I need to change my scale so that we see at least one full period of the sine wave graph. So what will be the period length? What's the period of sine? How long does it take a sine wave graph to repeat one cycle? I'll give you a hint. We use the unit circle to build our values for sine. So if I have a terminal arm here, and here's my y-axis, here's my x-axis, and I start measuring this angle here, theta, or better yet, x, and I calculate the values for x for sine, and I come up here, it starts at 0, goes all the way to 1, comes down here to 0, goes down to -1, and then comes back up to 0. Up to 1, down to 0, down to -1, up to 0. So what's the period of one cycle here? How many degrees? 360, yeah. So I'd need to see at least 360. Let's look at 720 degrees there in the x-axis. And there we go. Here is a picture of our sine wave graph going through 2 cycles. So we're seeing now 2 periods. So we can see here that if we start at the point 0, 0, I just trace this and come down. We don't need to meet these, so I'll shrink that. If we come down here, here's 90 degrees at 1. That's the maximum value of sine. And if I come back, here is the point 0, 0, goes to 1, comes down at 180 back to 0. Here is 270, and here is 360. So that is one period. The amount of time it takes to go through one cycle here. One period. And then we want to know, well, what's the equation of the axis of this? And this one is a parent function. It's untransformed. So unsurprisingly, the equation of its axis is pretty simple. What's the axis of this function? What's the midline for the top and the bottom? Yeah, it's just y equals 0. It's just the x-axis is its horizontal axis here. We would get that by taking 1 and subtracting -1, and that would be 0. Just the difference between those two. It's right at 0. And then the amplitude of our untransformed sinusoidal function. The amplitude there is how far is the top or how far is the bottom from that axis line. So what is that here? Suraj?
1.
It's just 1. Yeah. It's 1 higher than the axis right there. And it's 1 lower down here. So if I graphed that line, why am I graphing it? Y equals 0. So there is my axis line. And you'll notice that if we had another function that told me what's the distance between this and that line, it would be this function. So that is the amplitude there. Okay, so let's carry on. So, so there is some textbook things to practice here at 290, 1 to 6. But before I release you onto that, let's do our next lesson, which will be on the sinusoidal functions. We'll go very quickly through that one because we are not going to do the handout part yet. So here we go. If I asked you to represent the rotation of a bike tire and used the use some parent function. What type of parent function could you use here? So here's the question. Imagine that this is now no longer the unit circle, but that I have a rock stuck in my bike tire, and here are all the spokes, and the rock is stuck over here. Let's say the rock gets picked up right there on the ground. So here's the ground here. And then as I ride in this direction, I'm going this way, what's going to happen to the height of this rock as I ride that way? Yeah, it's going to start rising up as the wheel rolls this way. It's going to come up. It's going to reach a highest point, and then it's going to go back down again. So if I wanted to model the behavior of any one point on this wheel in terms of its height, what type of function could model that? Siraj.
Sine function.
Yeah, sine function will model that. Yeah. It'll model it very nicely too. It's going to start from its minimum and start rising. It's not exactly a sine function. We do need to change its phase shift and change the starting position, but that will work fine. You could also use negative cosine, would be the most efficient, because cosine would start at 1 and go down. This would start at -1 and go up. But it's not -1, because where's my axis here? Well, the axis is actually the axle, because that's going to be the midpoint for how high it goes. So that would be the midpoint. This would be the axle. And then the amplitude would be given here with the radius. So anyway, you're going to be thinking about that as we go through these ideas. So with sinusoidal functions, what we want to be able to do is sketch the graphs for sine and cosine and use the unit circle to do that. This is an activity that we will do tomorrow with the handout in your hands. And you'll sketch f of x as sine x and g of x as cos x and state their properties, the amplitude, period, and the equation of the axis, the domain and range for the sine and cosine graphs. These are our goals, to really understand these. So sinusoidal functions are transformed trigonometric functions for sine and cosine, and you can think of them as repeated oscillations or waves. So you have an interesting animation there. I'll show you a video with some really neat animations just before break today. So the unit circle is something that's going to be very useful to us to generate our curves for sine and cosine. We have these special angles, 30 degrees, 45 degrees, and 60 degrees. And I learned a really cool trick for remembering these. I'll show you in just a moment on the board. And they have exact values for the different trigonometric ratios through here. Jackson?
So looking at this circle here, it looks pretty important. So
Yeah.
would there be like a printout of that by chance?
Of this circle?
Yeah.
What if I told you that you could remember it using your hand? Let's do this now. So I just learned this trick. I didn't know it before. I know it now. It doesn't help me remember anything new because I know everything already anyways. But if you're struggling to remember your, I'm trying to be ironic. I'm trying to be self-deprecating by being super conceited. I don't remember everything, so maybe I would find this trick useful at some point. Take your hand, particularly your left hand, and imagine that you have here your thumb, your index finger, your middle finger, your ring finger, and your pinky. Okay? And now you're going to stretch them out so that this one is rising at about 60 degrees, this one at about 45 degrees, this one at 30 degrees, and this is and then you want to stretch your pinky out so that's your x-axis and this is your y-axis. So this is 90 degrees and this is 0 degrees. Okay? And now we want to remember these ratios. So I'll show you how you can generate these ratios for those points throughout here. So if we're looking at 0 degrees, then to find the sine of that, well, actually, let's take a look at the cosine for. Let's take a look at 90 degrees first. So you're going to look at your thumb. And to find the sine for any particular finger is you take the number of fingers that are to the right of that finger, and you're going to put that under a square root over 2. So here, for the sine of this, I would count 1, 2, 3, 4 fingers. So that would be 4, but I take the square root of it and I put it over 2, and that's the sine for this. So sine 90 is square root of 4 over 2. What's the square root of 4 over 2? 1. Because this is 2, and then I divide 2 by 2, and then I get 1. Yeah. So, yeah, you are right, just not right all the way to the end. And then to take the cosine of any particular finger, any particular angle here, you count the number of fingers to the left and do the same thing. So there's no fingers to the left of my thumb. So cosine of 90 degrees will be the square root of 0 over 2 is just equal to 0. So there's the cosine for this one here, 0. Okay. Now let's try another finger. Let's try the 60-degree one. First, let's do the sine of that. How many fingers are to the right of that finger here for 60 degrees? 3. So put 3, square root 3 over 2, and that's a sine of 60 degrees. Now, how many fingers are to the left if I want to do cosine of 60? Just 1. Yeah. So cosine 60 would be the square root of 1 over 2. What's the square root of 1? Find me 2 numbers that when multiplied together give me 1. 1. So square root of 1 is 1. So cosine 60 is 1/2. And there it is there, 1/2. And then square root 3 square root over 2. And now for the middle finger here, one of the middle finger's special properties is it has the same number of fingers on this side and that side. That's the point where sine and cosine are the same. And there's 2 fingers on either side, so I would have the square root of 2 over 2 for both sine and cosine. Okay. And it's the same process here for the ring finger, 30 degrees. And you can even get your fingers at like pretty darn close to 60 degrees, 45 degrees, 30 degrees, and then 0 and 90. It's pretty cool, eh? It's neat. I just learned this weekend when I was looking at videos for all of you. It's neat. Hey, you never forget it now. Can you use that, Jackson, to remember these values? Are you going to carry that with you wherever you go? Not mine, but yours? Yeah, you're right. Yeah, there you go. So it follows you wherever you go. So you can use that hand trick to remember these values of sine and cosine, at least for the 0 to 90. But then going around the circle, we can apply our cast rule, where down here cosine is positive. Up here, all of them are positive. Over here, sine is positive. And then down here, tan is the only one that's positive. So we can use that to generate values for the trigonometric functions. We can look at the y values, the x values, and think about our sine is opposite over hypotenuse. Yeah, I don't know where our bucket went. Okay. And in fact, if we go over to Desmos and take a look at that, we'll notice that if we're looking for like the value 1/2, and we want to know where does this equal 0.5, well, it's at 30 degrees. So that's 30 degrees. That's the value of sine is 1/2. We would get that by saying, well, how many fingers are on this side? So it's just 1. So it's wait for sine. Yeah. Yes, it's 1 over 2. Yeah, it's 1 over 2. So that works. Yeah. And then the value of 1 over root 2 when I'm at 45 degrees. Well, that's up here, 45 degrees. Now 45 degrees is about 0.7. 0.707, that's the 1 over the square root of 2. Square root of 2 is 1.4 something, so it's a little bit bigger than 0.7 when I do 1 over that. And if I also graph here, g of x equals cosine of x, you'll notice here, this is the cosine curve, and they cross at 45, because they're the same there. And this one reaches 0 at 90 degrees, and reaches the bottom of its period down there at 180, -1. So there's our cosine curve. Their intersections is going to happen at the spots where they're the same. So 225 and 45 are the places they touch, or 360 plus 45, which is 405 here. And then 360 plus 225, so that's 585 down there. And then continuing on, we'd see that pattern repeated for infinity, because the domain of this function is x's of the reals. We can put in any value for x, even very big values for this angle, and still find something to look at out there. Oops, wrong spot. So that's where we might see the unit circle. So tomorrow what we're going to be looking at is, and I will have, you'll see over here, oh, it's not that one. These ones? No, this one. No, this one. So this is the activity that you'll complete tomorrow, graphing the sine and cosine. And yeah, Jackson, you're going to fill in a unit circle yourself, so you'll have a copy of it there, and you'll use that to generate your curves. And you can use your hand to build your unit circle now. Okay. So here is a visualization. If we take a look, I'll present that. Here's a visualization of the unit circle. And as the unit circle goes around, if we think about sine is a representation of how high is this point at different points in the rotation. You see the angle is increasing here, and as it continues to increase, the height of that point oscillates. If you look over here, this is looking horizontally from like top down at what's the x value of those. And then it's translating those just by rotating at 90 degrees there so that we can represent the horizontal displacement of that point vertically as an output. So that's where we get the cosine curve there. And that sine, we don't need that little trick to represent it as a function. Sometimes you will see in the video I show you, they'll show cosine going up the y-axis instead, so they can graph it that way. But yeah, this is how we generate sine and cosine using the unit circle. This is effectively what you are doing. So these are hard things. You can't do this on paper, but you can do it in your mind if you practice visualizing these curves and practice visualizing the unit circle. So this is something for tomorrow. That's something for tomorrow. And then we'll take a look tomorrow at how we can then model things like Ferris wheel problems. If Billy is on a Ferris wheel and he gets on the Ferris wheel when the Ferris wheel is at like a 30-degree inclination and he starts riding it, create a function that represents Billy's vertical height, or a function that measures his horizontal displacement from the axis. We'll learn to use transformations tomorrow to model that type of behavior. Or take a look at the properties of this bike tire and how that's going to change the period, amplitude, and so the cycle of these different sinusoidal functions that we could create to model these types of behaviors. And so those are our ideas. There's the textbook questions, page 290, 1 to 6. There's also a Delta Math for today where you're going to start investigating these functions. And one video that we'll take a look at right now, just as some edutainment for this topic. So any questions you have, definitely contact me by email, and we'll be continuing these investigations after the break as well with terrifying transformations.